Okay, in this video we're going to walk through a couple of examples in non-isothermal batch reactors. So we're going to consider first a liquid phase reaction, A goes to B, where we have a rate law R equals Ka in a constant volume batch reactor. Now the reactor we're going to assume is going to operate isothermally, but we still have to calculate now the heat load as a function of time that's required to maintain it in isothermal conditions. So the species balance equation for a batch reactor is going to be that the derivative of the number of molecules of A in the reactor with respect to time is minus the rate times V. Okay, so minus because we are consuming reactant A. The stoichiometry is going to give us that the number of moles of A at any given time is the number of moles of A that we started with times 1 minus the conversion. So we can combine this, put this into our species balance equation, and get an expression for the concentration and the rate law. It all simplifies down to this. We've been doing this for a couple weeks now, so these things are probably pretty familiar. The initial condition on this equation now is that x at time 0 is going to be equal to 0. That's my conversion. And remember, what we wanted to do was to, of course, we have to find x as a function of time, but we also wanted to find q as a function of t. Okay, so if this is x as a function of time, as a sort of exponential going from 0 up towards 1 with rate constant k, then we have now to go through and do an energy balance. Okay, so we have just one reaction, so this is going to be quite a bit simpler than the sum over all reactions happening. We have an incompressible fluid because it's a liquid. The two equations that we can start with really become the same thing in this case. If we start from this special case, for example, also it's a liquid, and so we have that CV is equal to Cp. And that the delta would have just been equal to 0 anyway. So that one becomes the same as the one above. Okay, so this is a special case where the two special cases become the same thing. So we could start from here. Cp and Cv are the same. If we come down here, we've got a heat capacity, constant volume, constant pressure, the same. Rate times the heat of reaction, and that should be all equal to Q over V. Okay, so now what we're going to do is simplify this and solve for the value of Q as a function of time. Q should be equal to V times delta H of reaction times K. I'm just plugging in all of this stuff right here is coming from my rate law that was right there in the expression above. At the end, we end up with Q equals Q naught e to the minus KT, where Q naught is the initial rate at which it has to be removed from the reactor. So notice the sign convention here. When the heat of reaction is negative, that means you have an exothermic reaction. You're going to get a Q naught value and a Q at all times that's going to be negative as well. So that's generating heat within the reactor to maintain isothermal conditions. You have to remove it, and so that's why it has a negative sign. Okay, in this example, we're going to think about a liquid phase reaction, again, in a constant volume batch reactor. Again, we have a reaction A goes to B with rate law R equals Ka, but this time we have a heat exchanger, and it's given some specifications. We have an area A, heat transfer coefficient H, coolant temperature Tc, and we're going to give equations for the conversion X and the reactor temperature as a function of time. We're just going to go as far as to set up our equations and non-dimensionalize those. So the cooling liquid comes in at temperature Tc. Our heat exchanger equation is going to be something that looks like this all the time. And it's not necessarily going to maintain this thing at isothermal conditions. It's certainly not adiabatic either. This is going to be one of these cases where we can get something in between. All right, so let's start from the beginning. Our species balance equation says that we have dNA, number of moles of A with respect to time, is changing according to minus R times V. We can go through and do exactly the same kind of steps that we did before. dx dt equal to K times the rate constant is a function of temperature times 1 minus X. Okay, this is what's left of that species balance equation after some simplification. The energy balance equation, quite a bit more complicated. In this case, we get, we're in a liquid phase reaction, so we're going to have incompressible components. We're going to start with that first equation in the list above. Let me go up there, make it a habit for you guys to do that. We're starting with this equation, right here because we have incompressible reactor contents. All right, so if we go down there and plug all of this in, we get Cp times dt dt plus K as a function of T times A naught times 1 minus X. There's my rate law. Then we have our heat of reaction in here. And then this is the Q over V term right over here on the right-hand side. So notice the form of the Q term here. It's the heat exchange coefficient times the area multiplied by Tc minus T. Now I want to make sure, and this is a good habit for you guys to do as well, to go through and do a couple of sanity checks to make sure that we got the signs on all of these terms correct. Okay, so there's not much we can do to get this one wrong, but the others should be compatible with that. Okay, so let's consider the case where we have HA is equal to 0, so we basically have no heat exchanger in there. We have the heat of reaction is less than 0. In this case, we have an exothermic reaction. We have no heat exchanger, and so the temperature should be going up as time goes on. And indeed, that's what the sign convention that we've used here does. Okay, so that makes sense. We apparently have the correct sign on this term because of that. Okay, so in the next test, we can check the case where delta H of reaction is 0. So the reaction is neither exothermic nor endothermic. And Tc, the cooling liquid, is coming in at a temperature colder than the reactor. So if that's all working correctly, then intuitively what should happen is that the temperature in the reactor should be dropping. And if we go back here and we look, indeed when Tc is less than T, this term right over here is going to be negative, and that's going to make this time derivative, this temperature derivative with respect to time less than 0. Okay, so that checks out. So apparently we have the correct sign also on the Q term. Okay, easy to mix this up because you write T minus Tc here and everything goes terribly wrong. All right, so now what we're going to do is non-dimensionalize these. We're going to start with, we're going to non-dimensionalize everything by lots of different ways to do this, but we're going to start with the initial temperature, T naught, and we're going to define a dimensionless time, tau, is equal to K at the rate constant at T naught multiplied by T. We have a dimensionless temperature that we're going to use, which is going to be T divided by T naught. A couple of other convenient things to define, the theta sub C, which is Tc over T naught, and theta 0, which is T naught over T naught. It's just one. Then we're also going to define a dimensionless rate constant by taking kappa as a function of theta is just K of T over K of T naught. Okay, from this point now we go through and we non-dimensionalize and we get that dx d tau is equal to K of theta times 1 minus x. That was just the species balance equation from above. The other one ends up being d theta d tau is this big dimensionless parameter right here, which has to do with the heat exchanger properties relative to the heat capacity of the mixture, multiplied by theta c minus theta. And then there's another dimensionless parameter that shows up in here. That's this one, which has to do with the heat of reaction divided by the heat capacity of the mixture. And then this is, of course, my reaction term over here. Okay, there's one more dimensionless parameter buried inside this expression. Down in here, in the kinetics, the rate constant for this process, there is an activation barrier that has to be non-dimensionalized as well. Okay, so we won't go through and put in numbers for these things, but you can see that really you end up taking something that had 7 or 8 parameters and ends up reducing it down to just 3 dimensionless numbers.